All right, this variable star lab can sometimes be a little overwhelming. It's a lot of information. So I'd like to just introduce you to the key elements of what's happening here. The reason I really like this lab is because it connects a lot of dots for us in terms of how CCD cameras work, how we really truly analyze images in astronomy, and then what we can learn from those images, especially as it relates to variable stars. What I'd like you to do is read through this student guide and work through this student guide, but I'm only going to ask you to actually submit something here at the very end, which is a lot of this guide is actually what I'll show you here in the video, so you can probably kind of skim it. But what I'd like you to submit ultimately in the end is you're going to find 4 variable stars. There's one that I'll show you, and then there's 4 other variable stars. You're going to find them, their x and y, and then you're going to figure out what the period is of that variable star and its amplitude. That is, how much is the star varying in brightness and how long does it take to vary in brightness. And you'll graph that, and then based on what that graph looks like, you'll be able to tell me what type of variable star it is and give me some explanation of what that means. Okay, so just this page and this page is what you'll actually submit for this lab. But let's go through how this all works. So you'll start with a little bit of background reading, and the first thing you'll read about is how there are different kinds of variable stars. In particular, there are variable stars that are just single stars that actually kind of pulsate and vary in brightness. And then there are also variable stars, what we call variable stars down here, which are actually 2 stars that orbit each other and briefly eclipse one another. And their light curve, that is how the brightness changes with time, looks very different, so we're able to categorize them. You can see here for eclipsing binary stars, you'll see that the system of 2 stars maintains a constant brightness until one gets eclipsed, has a sudden drop in brightness, and then stays again constant brightness until the other one is eclipsed. And so they have these kind of like eclipses where they drop in brightness. For a single star that's a variable, we see instead a very different pattern where it's fluctuating in its brightness, getting brighter and dimmer and brighter and dimmer. In particular, there's 2 different kinds of variable stars that are actually truly individual stars. One is called RR Lyrae, the other are Cepheid variables, and their biggest difference is how long their period is. So an RR Lyrae will actually pulsate, every hour or two, so many times a day, whereas a Cepheid variable pulsates much more slowly. And these 2 types of variable stars are useful because their variation in brightness, the period of their variability, actually tells you something about the intrinsic luminosity of the star. So you can actually use them to measure distances. Okay, but what we'll do is try to characterize these based on their period and the shape of the curve. Okay, so you can read some background on there. The other piece of the puzzle here is trying to understand exactly how CCDs work. And there's a variety of things that this introduces. A couple of the things that I just want to highlight, one of them is this idea of the bit depth of a CCD. And this is true of all digital images, that the bit depth, that is how many shades of gray, and we talked a little bit about this when we were actually doing CCD stuff with Hubble images. If I have a bit depth of 2, that means there's only like 4 possible different shades of gray, right? 0, 1, 2, 3, and 4. Whereas if I have a bit depth of 6, then I can have, well, typically 8 is a more common number. I can have 256 shades of gray. And in most astronomical images, it goes all the way up to 16, right, where I get like 65,000 shades of gray. So a ton of information. I just want to show you another way of visualizing this idea of bit depth. Typically, a black and white digital picture would look like this up here. If you were to have 8 bits, that's 256 possible shades, and it looks pretty normal, like this is what you'd expect to see. It looks like a high quality picture. As you reduce the bit depth to 4 bits, you only get 16 possible shades. You can certainly still tell what it is. But as you reduce the bit depth further, it gets to like newspaper print kind of thing, where you only get like a few shades of gray, until the point where you only get black or white, or gray and white. Okay, so that's that idea of bit depth. You'll read a little bit about that. All right, now then it walks you through a series of simulations which really mirror what astronomers have to do. So if we were trying to discover variable stars in real life, we'd go out, we'd take pictures of the night sky. But part of the problem is when you take these pictures, they don't lie on top of each other. Right? The camera moves a little bit, the telescope moves, and so if you were just to put them right together, you'd have to actually line them up with each other first. Okay, and that happens. We have tools in astronomy to help us do that. You don't actually grab the picture and move it around. You can kind of automate this process. But the thing to keep in mind is that it has to be lined up, right? So if I make one of these transparent, you can see that the stars don't line up. And if I want to measure the same star in every picture, I have to make sure that all of these pictures line up. We call that registering or registration. Okay, so I got to line up these pictures. You see, oh, there, now the stars line up. Okay, so what ends up happening is you end up only being able to use a portion of the actual image where they actually line up with each other. Okay, that's registration. Now, the second thing we do is after we get all the pictures lined up, if we want to just kind of find the stars, the variable stars visually, we would do a blink comparison. Basically, we take those pictures and we play them like a movie, and that allows us to actually see if anything's changing in brightness. Of course, they have to be lined up on top of each other, that's why we have to do the registration first. So if I add a bunch of these guys to my blink comparison here, okay, I'm going to add them to my little video, okay, and I blink them. You see it's going picture to picture. And if I look at this a little carefully, I can see, hey, look, I see some variable stars. Like right here, next to my cursor, that star is getting brighter and fainter. Brighter and fainter. And look, I see another one here. It's a little brighter and then fainter again. Okay, so I might want to add more pictures here. And because some of these might be variable much more slowly. Right? And I can make the video go faster. Okay, and so this is a way where you can find, I see another one up there, you can actually find the stars that are variable, right, using this blink comparison. Now the example I'm going to show you will do this variable star right here, located at x equals 64, y equals 114. Okay, but you got to find the other variables and characterize them. Okay, so the blink comparison is a visual way to actually find the variable stars. Now, once you find them, we don't want to like measure their period just by looking at it with our eyes. We actually want to extract data from the images. And that's what the process of photometry is all about, is extracting data. The way we do that is we use these things called apertures, right? We want to actually literally measure the brightness of a star. And so if I take this aperture and I hover it over this star, this is kind of how astronomers would do it. And again, we do this with computers almost always. Well, always. We get it lined up. Come on. There you go. Okay, now here's how this works. This is what the aperture does, and this is what the computer program does. It takes all the pixels inside the inner circle, and it adds up all of the counts. So, or it finds an average, right? So you see it added them all up, 311,000, takes the average value inside. But now you see that some of that light's from the star, but some of it's also just background noise from the sky. And so that's what this outer ring is for. The outer ring adds up all the counts on the sky, not on the star, and takes the average there. In which case, the difference between the light inside and the light outside, that is the average counts inside and the average counts outside, gives us a real measure of how much light is coming from the star. And that's a number then that we actually use to calculate the magnitude. So I would do that for the star I'm interested in that's a variable, but then to tell if it's variable, I need to compare that to a star that's not varying in its brightness, right? Because there might be little fluctuations, some haze goes over the sky, a little cloud, and that's what causes the star to get darker. Well, I compare that to a star that appears to be constant brightness so that I can actually tell how much is my variable star really changing compared to this other star. Right? That way if a cloud goes by, they both drop in brightness and it gets removed, right, from the image in effect. Okay, so this is how photometry is done. Now typically, when astronomers do this, this process is somewhat automated. You tell it where the variable is, it goes through all the pictures, and it pulls out the data, and you make a graph from it. Right? And that's exactly what we can do with this variable star photometry analyzer. Okay, so I can pick a comparison star and a variable star. So let me start by picking a comparison star. I think this one is constant. Okay, and then I have a variable star. And what's already been done for us is all the pictures have been laid on top of each other. When I click on this star, it's going to go through every one of the images. It's going to pull out the data and put it in a graph. Okay, now these pictures were taken over the course of about 25 days. Right, so I have a graph here which is showing the change in brightness, the difference between this star, my variable star, and the constant star. And it's showing that over the course of 25 days. Now I can see that this star, its brightness changes very quickly. I mean, even in one night of data, it's changing by like half a magnitude. It's changing really dramatically. And what I want to do is figure out how long does it take this variable star to go from being bright to faint and bright again. Now the huge problem is that the Earth rotates, and so I can't watch the star for 24 hours. All I can do is watch it at night. In order to find out when does it get back up to its regular brightness, I have to watch it night after night after night and try to put it all together and try to piece together its light curve, how its light actually changes. But this can be done. What we do is, instead of just graphing the brightness of the star over time, because I can't, I could try to draw some squiggly lines in here, but I don't know that I'd actually get it right. You know what I'm saying? It's actually kind of tricky. So what we do is we plot the phase. And what this is exactly what astronomers do. What they do is they guess a period. They would say, well, let's just say the period of this oscillation, this variable star, is 7 days. And so every 7 days, I just reset the graph and plot again and plot again and plot again. And then if all of them fall on top of each other in a beautiful little pattern, then you know that you found the right period. Okay, so this is not the right pattern because this is not what a variable star would do like that. Okay, what I want to see is just one oscillation from bright to dark. And so this graph at the bottom is sort of an advanced math tool that can help astronomers get a really good guess. And what it does is it graphs sort of the likelihood that a given period is the right period. Now, when I just look at this graph the first time, I can see that it's varying over the course of just a single day. I mean, one night it's going from bright to dark. So I know if I slide my period guess here, this is in days. I'm at 4 days right now. I know it's got to be less than 1 day, right? Because I'm just seeing it change in brightness so quickly. So I'm going to zoom in around this, okay, and look a little more carefully at what this graph shows me for periods less than 1 day. Now, when I change the phase here, okay, I'm starting to see more interesting things happening in my graph. So I'm going to keep the graph on phase now. Now what this graph shows, the likelihood of these being the correct phase, the lower the curve is, the lower the graph is, the more likely that is to be the correct period. So if I slide this over to this little low point right there and zoom in, okay, this is a more likely, and you start to see, okay, now I'm starting to see a pattern here, right? But it's not very tight. I should see all of the data lie right on top of each other. Show me what it looks like. So I'm going to zoom out. Now here's the lowest point on my graph down here. Let me go check that out. So this is probably one of the best guesses that I could try for the period. 0.31 days. Okay, if I zoom in, oh, you see, look how it's kind of coming together, right? So I'm going from bright to dark to bright. And because I'm resetting the data every 0.316 days, all the data lays right on top of each other. And this is showing what the light curve looks like. But to get exactly the right period, I want all this data to lie as close as possible. So maybe right there. Now that is what the light curve, if I could just sit and watch this thing nonstop, this is what it would do. Up and down. You see it keeps repeating it over and over, which is why all the data can lay right on top of each other. Now I should just double check and see if anything's better. Like I'll check this one over here. Is this one, does that get the data any closer? No, it's more spread out. So I think this really is the best period. All right, so this is where I would go to my graph, okay, and I would go over here on my lab, okay, and I would say this is variable number 1, okay, so I've done this one for you. I would say its x and y position is 64, 114. Its period appears to be 0.3171 days. The amplitude is something like, in fact, I could show the difference tool here. From top to bottom is 0.6 magnitudes. I would graph kind of what it looks like here on my chart. Now I have to say, what type of variable is this? Well, let me look back at this variable introduction page right here. And I'd say, okay, do any of these look like what I expected? Okay, so this one tells me that I've got 3 types here. On the top is one type of RR Lyrae, the middle is another type of RR Lyrae, and the bottom is a Cepheid. And you'll see Cepheids always have this really characteristic shape. Okay, so this must be a type of RR Lyrae, and I also know it must not be a Cepheid because the period is less than 1 day. Right? So this must be an RR Lyrae. And I'd say, how do I know? Discussion classification. I know because the period is much less than 1 day, and it has a shape characteristic of an RR Lyrae. Okay, so you would repeat just this process where you find the other variable star, you make a graph, and then you try to characterize what kind of variable is it. And in the process, you're really doing exactly what astronomers do when they do photometry and analyze variable stars. All right, I hope that helps.